So let us consider the combined gas-steam power cycle shown in the figure below. The topping cycle is a gas turbine cycle that has a pressure ratio of 8. In this cycle, air enters the compressor at 300 Kelvin and the turbine at 1300 Kelvin. The isentropic efficiency of the compressor is 80% and the gas turbine is 85%. The bottoming cycle is a simple ideal Rankine cycle operating between the pressure limits of 7 megapascal and 5 kilopascal. Steam is heated in a heat exchanger by the exhaust gases to a temperature of 500 degrees. Knowing that the exhaust gases leave the heat exchanger at a temperature of 450 Kelvin, determine first the ratio of the mass flow rates of the steam and combustion gases, and also the thermal efficiency of the combined cycle. I know that in this problem there is some new concepts introduced, but don't worry, in the exam I will not introduce any new concept. And if I introduce something new that we didn't tackle together in the problems, I will explain it directly. And for example, let us say we didn't cover together for a gas how we use the tables, okay? So here I can tell you, for example, since you have a gas, from tables, it's a little bit different than tables of water, okay? In tables, you can read U, H, but you don't have the entropy S. But instead of it, you have what is called the reduced pressure and the reduced volume. And also in the exam, I will provide you with the thermodynamic tables because you know that depending on the book, these tables will vary from one book to the other. That's why I will provide you with thermodynamic tables in the exam. And you don't need to print anything, okay? So I will tell you then, if you have an isentropic process for air, you can use that during this process, PR2 over PR1 equals to P2 over P1. If I give you this information, this will help you to solve your problem. هلا we'll see how. So I will give you this information, plus also I will introduce to you what do we mean by the isentropic efficiency, okay? So whenever we give you an isentropic efficiency, I will give you directly the formula for it. The isentropic efficiency means the following. In the majority of problems we did, we always consider that whenever we go through a pump or through a turbine or through a compressor, that we have isentropic process. So S inlet equal S exit. But in reality, this will not always be the case, okay? That's why when I give you the efficiency, you can calculate the actual enthalpy at the exit. And for example, if you consider the compressor, okay? So for the compressor, if we look at the figure here, what do we have? We have that point, the inlet point is 1 prime, okay? And the exit point is 2 prime. So we are used to say that if we have an isentropic compressor, I go in a TS diagram, I have increase in temperature at constant S, okay? This is true if you have an isentropic efficiency of 100%. Then you can say that S1 prime equals to S2 prime S, okay? But in reality, it's not the case. In reality, we have losses and we have increase in entropy. So instead of having just S1 equal S prime 1 equal S2 prime S, we have a small increase in S. But how we can compute this increase? By using the formula of isentropic efficiency. And of course, I will give it for you in the exam. In case we give something similar, it will be very clear how to use it. I will tell you that the isentropic efficiency of the compressor is equal to H2 prime S, okay, minus H1 prime over H2 prime minus H1 prime. Okay, why we have this? Because in ideal case, if we don't have losses, the enthalpy change required is minimal. Okay, so you need to provide a minimal work on your compressor since there is no losses. But if you have losses, you need to provide extra energy. So actually 0.2 prime will have a higher enthalpy than 0.2 prime S. And to be able to calculate the actual value of H2 prime, first you work as you know, in general, what do? You find 4.1 the properties. Okay, we'll do it together. You get properties at 0.1. You say if the process is isentropic, I say S1 prime equal S2 prime S. But now, because for tables of gases, we don't have S, let us see together what will be the strategy to do to calculate H2 prime S. So if the process is isentropic, what is H2 prime S? Once I find H2 prime S, I know now H prime 1, H prime 2. All I have to do then is to replace the isentropic efficiency by its value, and the only unknown will be H2 prime. Okay, let us just go to the tables to understand more what we are talking about. What do we know in this problem? In this problem, first we have two cycles. Let us explain the system, then we go into the details. Okay, in the course material, in the last part of chapter 3, we said that we can create combined cycles, okay, of gas and steam. And the purpose of this combination is to enhance the efficiency, okay? How we can enhance the efficiency? You have the gas cycle, which has the configuration of Brayton cycle, consists of an open system. Why it's an open system? Because it's an open cycle since we introduce fresh air in the compressor. This fresh air is compressed to a high level to enter the combustion chamber. In the combustion chamber, we burn fuel. This will lead to release of heat. Okay, so we'll have then the hot gases of combustion will go through the gas turbine. And as they move through the gas turbine, you'll have the expansion process, which will lead to production of power. So we have at the level of the gas turbine, production of power W dot out. Okay, now the idea is the following. For gas cycles, the exhaust temperature is really very high. You have high temperature, high pressure at your exhaust. So if you just don't use this energy, you will have a very low efficiency because you cannot anymore, so these gases will be wasted and you cannot recuperate this energy. That's why to enhance the efficiency of this system, these exhaust gases, we will take them through a heat exchanger. And this is a type of heat recovery because instead of losing this heat, we pass these exhaust gases through a heat exchanger. And then we can take heat from these hot gases and give this heat to steam in the evaporator of a steam cycle. And if you want, this heat exchanger will be a common part between the two cycles. It will represent the evaporator or the boiler of the steam cycle. Okay, the steam cycle, which is the conventional Rankine. So here, by just combining an open cycle, which is called Brayton cycle, and a closed one, which is the Rankine cycle, we can enhance a lot the efficiency of both because instead of losing energy, okay, we can use some of this lost energy to drive another cycle. So no need to put a boiler here anymore. And there is no Q dot in here. So completely you will give heat completely from the exhaust gases to the steam. In case they are not enough, okay, sometimes maybe the heat extracted is not enough, then you can add a boiler, but then the load on the boiler will be much smaller. Yani Q dot N provided will be much smaller than the conventional case. That's why you will enhance a lot the efficiency. In general, open cycle, why they are characterized, why Brayton cycle are characterized by low efficiency? Because it's an open system and you reject gases at very hot temperature. But the advantage of this cycle is that it can produce a high amount of power. So it is used, for example, in aerodynamic applications to drive airplanes, okay? But the idea is that even inside, let's say, the airplane, you need, let's say, to have some heating needs, maybe water, or you need to drive another cycle. So you can benefit from these exhaust gases, and it can be used to produce electricity. So whenever you need to construct a power plant producing electricity, this is a widely used system because you will first benefit from production of high power from gas turbine, and you will benefit from the energy of hot gases to drive another cycle that also will produce electricity. So you can have a high amount of electricity produced. So you have W dot of gas turbine plus W dot of steam turbine, and you just have here one input. You just have to put an input at the combustion chamber. This is your only source where you put energy. So you can expect then to get a high efficiency when you combine these two cycles. So this is the idea of CCGT, or combined gas steam cycle systems, okay? Now, the analysis will be a little bit more complex than one cycle, but it's fine. And if we move step by step, it will be relatively simple. So I want from you to understand cycles, because I might ask you, for example, draw the scheme of combined gas steam cycles, or draw the scheme, let's say, of reheat or of cogeneration. So we need to understand these concepts to be able to represent their cycles. Okay. Now, what is a little bit new, as we mentioned, is how to deal with gas, because majority of problems we considered steam, and we worked a lot on steam tables. So here, what is new for the Brayton cycle is that we have a gas, but it's really simple. All you have to do is to go to the table. As I told you in the exam, I will provide you with tables, so don't worry about it. And in several books, the values will change, but delta H will remain the same. So whatever the tables you are using, you'll get the same results, okay? So now, if I go to the appendix of these tables, I can see that for air, the ideal properties of air are given in table A22. So I can just go to table A22. And as I told you, I will provide you tables. Don't worry about them. Okay, I will provide you the tables that you need. So once we go to table A22, we'll see that there is some difference between this table and the one we are used to with the steam. Okay, because as I told you, the input and the output is a little bit different. We know that for steam, we have temperature and pressure as input, while for an ideal gas, you just have to know the temperature. Once you know the temperature, you can get the enthalpy H, or the internal energy if it's a closed system, etc. So here, we know that the inlet temperature is 300 Kelvin. So we go to the table. This is T is in Kelvin in the table. So we just have directly 300. We can read automatically. This is H at 0.1 prime. So this is H1 prime. Okay. So now we know the enthalpy at the inlet of our compressor. Now, as I told you, in this table, we don't have S, okay? We have something different, okay? Which is S0 is not S, okay? So what we will use here, whenever delta S is 0, they are telling you in the table, if delta S is 0, so if you have isentropic process, then these are the values of PR. How you can benefit from this? In this problem, they told you that the compression ratio P2 over P1, the compressor ratio is 8. Okay. So all you have to do then, and if you go back to the given, okay, you know at the initial point what is the pressure. Okay. So I told you that at inlet conditions, you have for your compressor 300 Kelvin. Even you don't care about if you want the value of the pressure. You need just to know the ratio. Because once you put P2 over P1 equal to 8, okay? And as we said, it's equal for isentropic process. It's equal to PR2 over PR1. Now, from your tables, you can get PR1 because since you know the inlet temperature T1, the table will give you PR1, okay? So if I go back to my tables, I say, I know the temperature, I read for this temperature, what is the value of PR1? It's 1.386. So I replace P1 by 1.386. And then I say that if PR1 has this value, PR2 is equal to 8 times 1.386, okay? And now, from the value of PR2, you can deduce T2, because you will do it in the opposite way. Now I know PR. For each PR, I have one corresponding temperature, okay? So if I go back to my problem, when I calculate the value of PR2, which is 11.09, I go back to my tables and I try to search for 11.09 for PR, okay? So if I move down with PR here, I need to get for PR a value of 11. So you can see here I am in this column. My value 11.09 is very close to this one, 11.1, okay? So I can read then the corresponding temperature. So the temperature is nearly 540 Kelvin, okay? So this will be my T2, but T2S. Please remember, if the process was isentropic, I will get this temperature, okay? And if the process is isentropic, I will get this enthalpy H, okay? So now, after I get for isentropic process, what will be H? I use the formula of isentropic efficiency to get the actual H. So this is the whole idea about isentropic efficiency, okay? So I say the temperature is 540 in case it was isentropic. And I say H2S, okay? So here we add S and we add S. If it was isentropic, this is H2. But to get H2 real, I just say that W, the isentropic efficiency of my compressor, which is 80%, 0.8, is equal to H2S. H2, in the figure we named the point 2 prime, so H2 prime S minus H1 prime over H2 prime minus H prime 1. The only unknown here is H2 prime, so you can get it, okay? So this is the only new thing to know about air. And despite that, the method is the same. How we do interpolation, how we use tables, etc. So now if we go back to the problem. In this problem, we need to study the efficiency of the system. And we need also to know what should be, the first question is to determine the ratio of the mass flow rates of the steam and the combustion gases. Why we have a certain ratio to satisfy? We cannot work with any ratio because we want to just rely on the gas cycle to drive the steam cycle. So the mass flow rate passing through the steam cycle should not be very large, because if it's so large, the heat input will not be enough. Okay, so we say if we have a certain m dot of gas circulating in the gas cycle, what should be m dot steam, okay, in order to be able to completely drive the steam cycle with the gas cycle? So this is the question. We need to determine the ratio m dot steam over m dot gas. Whenever we have such a question, we need to write the energy balance for the heat exchanger, okay? Because for this heat exchanger, we have exchange of heat between the two streams. If they don't tell you anything in the problem, you consider your heat exchanger ideal. No, it will not produce any losses to the surrounding. So you can say that sum of m dot nhn is equal to sum of m dot out h out. Okay, so here you have for your heat exchanger 2 inlets and 2 outlets. So that's why you can simply say that what are my inlets? My inlets are 0.4 prime and 0.2. So when I want to put first for the inlets, I have m dot gas times h4 prime plus m dot steam times h2 is equal to summation of m dot out h out. So it's equal to m dot gas times h prime 5, okay, and a plus m dot steam times h3, okay. So this is what you can do, or you can write it in a different way. You can say that the heat, the amount of heat lost by a stream of the gas cycle is equal to the one received by the steam cycle, because what is lost by gas, the gas is gained by steam, because I told you we assume no heat loss to the surrounding. Okay, so you can write it in another way. You can say m dot gas times h4 prime minus h5 prime equals to m dot steam times h3 minus h2. So what is lost by gas is gained by steam. And this is how you can calculate the ratio of mass flow rates. Okay, so m dot gas over m dot steam is equal, okay, here's I asked for the ratio of steam over gas, so just to reverse it, m dot steam over m dot gas is equal to h prime 4 minus h prime 5 over h3 minus h2. Okay, so to be able to get these mass flow rates, you need to know the enthalpies at points 2, 3, 4 prime, and 5 prime. So let us do the analysis how to get the enthalpies at these different points. So first, as we mentioned, okay, between 1 prime and 2 prime, we did the analysis. Then we know that they told us about state 3. They gave us the temperature. And as we noticed for a gas, if you know the temperature, you can directly go and read the values of the value of enthalpy. So all you have to do now to get H3 prime is to go to your table. And from your table, at a temperature of 1300, okay, so here you have for a temperature of 1300, you can read what is the enthalpy. So here you can see that we have several values of temperature. This is the one that we want, 1300, and this will be the corresponding enthalpy, 1395.97. Okay. So now we know the properties at points until now at 1 prime, 2 prime, and 3 prime. Now, between 3 prime and 4 prime, it's exactly the same procedure that you did for the compressor, because they told you that for the gas turbine also you have an isentropic efficiency, but 85 instead of 80. Okay, just as I told you, I will give you in the exam the formula, but I would just want to explain it for you. For the turbines, the efficiency, the isentropic efficiency is opposite to the compressor. Why? Because when you compare real and ideal case, for the compressor, the ideal case will be to have a minimal input. Okay, so always the isentropic process will correspond to W compressor, W dot compressor minimum, because you neglect losses. So you just need the minimal energy to compress your air. While in the gas turbine, it's completely the opposite. Because if you have an ideal scenario, you will produce maximum energy. So you have W dot turbine maximum. That's why for the isentropic case, you have maximum work, while for the real case, the work produced by the turbine is lower. Okay, that's why the isentropic efficiency of the turbine is defined as H4 prime, H3 prime minus H4 prime over H3 prime minus H4 prime S. Okay, so it's exactly the opposite, because in the ideal case, the work is maximum for a turbine, while in the ideal case of the compressor, the needed input is minimal. Okay, so here, all you have to do is the same procedure that we did for the compressor. You say, I know temperature T3, okay? So since I know the temperature at 3 prime, I go to the table, I get PR at 0.3, PR 3 prime, okay? And I know that the ratio of PR 3 prime over PR 4 prime is equal to the pressure ratio, is equal to P3 over P4, okay? And in a Brayton cycle, you have the same pressure ratio for both, because you are operating between two pressures, okay? A high pressure and a low pressure. So also here the ratio is 8. So once you get PR 3 prime from the table, you deduce what is PR 4 prime, and from PR 4 prime you read T4 prime. T4 prime again, S, okay? The isentropic temperature. And you read H4 prime, S. But actually, you have a different value for H4 prime, okay? H4 prime is larger than H4 prime S. That's why you don't have 100% efficiency, okay? So once you find from the table H4 prime S, you replace in the formula and you get H4 prime. So it's the same methodology used in the compressor. Okay. Now, once we are done with this, we have H at point 4 prime. At the exhaust state, they told us that the temperature of exhaust gases is 450. So all we have to do is to go to the table and read for 450 what is H5 prime. And then we are done with the Brayton cycle, the analysis of the different points. Okay. And concerning the Rankine, you are familiar how to get the different points, H1, H2, H3, H4. So it's always the same procedure. Now I am ready to answer all the questions that they want me to go over. Okay. So first, I replace the enthalpies, I get the ratio of mass flow rates. If we do this, we'll see that this ratio is relatively small, and we can understand this because we are driving Rankine cycle purely by the gas cycle. Okay, so this information will tell you that if you have 1 kilogram of exhaust gases, you can heat only 0.131 kilogram of steam. Okay, and if you want to heat more, then as I told you, you should add a boiler. So you cannot use only the combination of the two cycles. You need a boiler to produce extra input, okay? But now we don't want this. In this problem, we just want to have no boiler added. So we can just circulate only a ratio of 13.1% of steam compared to gas, okay? And we want to study for this ratio what will be the overall efficiency of the two cycles combined together. So here, to see the importance of this combination, we can calculate separately the efficiency of the first, the efficiency of the second, and the efficiency of the combined cycle. Okay? So first, let us just look at the figures. If I just tell you calculate the efficiency of the gas cycle, in the gas cycle, your only input is Q dot N, okay? And your output is W dot net, which is W dot turbine minus W dot compressor, okay? So you have to evaluate these terms, and as usual, the technique is always the same, okay? So let us put it here. So W dot compressor for the gas. So the thermal efficiency of the first cycle will be equal to, what is W dot net? If we consider, okay, per mass flow rate, per unit of mass flow rate, because M dot will cancel out. And you have M dot in the numerator. It's M dot times, for W dot turbine, it's H3 prime minus H4 prime. While for the compressor, it's minus H2 prime minus H1 prime, so plus H1 prime, because minus minus, over Q dot N, which is M dot times H2 prime, H3 prime minus H2 prime. So this is how you can evaluate the thermal efficiency of cycle number 1, if it's alone, if it's operating alone. And you will see that you'll have a low efficiency, as we discussed before, because it's true that these systems can produce a high amount of power, but also we are losing a lot of heat that is unused because of the high temperature and pressure at the exhaust of the gas turbine. So this is why we'll combine it to another cycle. Now, if we study the Rankine alone also, you know how to do it. It's also W dot net over Q dot N at the boiler level. You can compute it. But now, to see the improvement, let us find the overall efficiency of the combined cycle and compare it with the efficiency of each one alone.